A popular approach for explainable machine learning in general, not just neural networks, not just CNNs, is known as LIME. LIME stands for Local Interpretable Model Agnostic Explanations. So each of those words means something which should become clearer when we explain the method. The way the method works is to approximate any underlying model by an interpretable linear model. Let's see how it does that. So you first have a trained model, and now you're going to train an interpretable model on top of some small perturbations of a given instance. So here is an intuitive visualization of the LIME approach. So the blue and pink background here give the black box model's decision function f. So that's the classification boundary that you have between two classes. Let's assume it's a binary classification problem, and all of these pink regions correspond to one class, all of these blue regions correspond to the other class. The bold red cross is one specific test instance that you're given, which you have to explain. So I have been given an image, for instance, of a cat, and I now have to explain, and let's assume that this is the decision boundary of a CNN. I now have to explain why this red cross is called a cat. Okay, so that's what we've been talking about so far. This is just a different way of viewing the same problem. And finally, you also have a dashed line here, which is a learned explanation. Now let's see how this explanation is learned. The way it is learned is to take this bold red cross, which is a given image, construct a few perturbations of the image. So you could now take an image, occlude a part of it, occlude a segment of it, occlude an object in it, whatever it be. These are different kinds of perturbations that you construct around the image. And you notice that when you remove a certain portion, our model classifies it as positive, and when you remove another portion, our model classifies it as negative. And that's why you see these plus reds and these blue dots, which means those respective perturbations were classified by our model as belonging to class 1 or class 2. So you should be able to intuitively understand now how this can be used. If I know which perturbations are making me lose the class label and make it go to another class, you know that they are my most important regions in the image for a particular class label to be assigned to that image. Let's see this in more detail. So given a point x, that's your bold red cross, let z prime be a point obtained by perturbing one dimension or region in x. So you could perturb a pixel, or you could perturb a particular region. You could do occlusion kind of experiments, or you could just perturb an entire region of an image. And capital Z is the set of all perturbations. Let's assume that we have some metric pi x of z prime, which is a proximity measure between instances z prime and x. So for example, if you take this the not bold plus and the bold plus, the distance between them is what we're going to refer to as pi x of z prime. This could be a distance metric such as an inverse exponential distance metric. So you could have an exponent of minus d xz prime whole square, where d is a squared distance, divided by some sigma square, which can be predefined by a given user. F is again the model being explained. Our goal now is, given these perturbations z prime and your original image x, we want to build a model g of z primes such that g of z prime is equal to wg into z prime, which is the linear model, such that the output of g of z prime is the same as the output of f of z prime. So which means we want this to be also equal to f of z prime. What do we mean? Remember that f is this function that's already given to us. G is this linear model that we are trying to develop using only those perturbed examples, and we are saying now that g should be learned in the neighborhood of x in such a way that it makes the same decisions on all of these perturbations that the original model would. on those if you gave those as inputs. So in a sense, G is like a local approximation of F. F is what occurs across the domain of the inputs. If we take a particular example and perturbations of that example around its neighborhood, then G would be a linear model that approximates the original decision surface of F in that local neighborhood. Now we want to learn WG. That would be our goal, because we want to learn that linear model. WG is learned by minimizing. You take two Z and Z primes belonging to Z, pi x of Z, which is the distance of x from Z, f of Z minus g of Z prime. So you want to ensure that the decisions of F as well as the decision of G are together, they make the same prediction, and you also want to keep in mind how far Z is from X. So if it is very far away, you can perhaps allow it to make a little bit of mistake, but if it's close by, you don't want to lose anything in the decision at all. That's the loss function that we use to learn G of Z prime. Let's see how this is used. So given an image such as this, so your perturbations could be where you take, let's say, the face of the dog and remove it and give the rest of the image and see what the network predicts as. Similarly, you may remove the strings in the guitar and see what the model predicts as. Similarly, then you remove your the board of the guitar and you would see what the model predicts as. And based on all of these, if you learn a G the way we talked about it, you would get your WGs, which would tell you how much each of these Z primes weights towards these decisions. In a sense, that tells you which of these Z primes is most important for a particular decision. Rather, you would be able to say that these are the regions in the image that are most important to call this image as corresponding to electric guitar. These are the regions that are most important to call this image as corresponding to acoustic guitar, and these are the regions corresponding to this image which correspond to the label Labrador. Lime also has a fidelity slash interpretability trade-off, and the reason for this is the loss function that we used tries to ensure that the function G, the linear model that we learn, should be approximating F in the locality defined by pi of x. So the goodness of function G is very important. At the same time, you also don't want G to be too complex a function. So G ideally is a model that belongs to the class of all interpretable models. So a simple example would be a linear model. And we define omega of G to be the complexity of the G model. What do we mean by complexity? If we are using G to be a decision tree, it could be a depth of the tree. If we are using a linear model, it would be the number of non-zero weights. If we are using it for image-based analysis, we may simply say that the number of superpixels should not be greater than a certain amount. What is a superpixel? A region. Okay, superpixel is just a region of an image. We wouldn't want more than 3 to 4 regions to be non-zero in that model when you make your decision. Remember in this case that G is a specific model learned for only one image, that bold red cross that we saw. If you gave a different image, you'll have to learn a different G. Okay. So this is the complexity of the G model. In the earlier example that we talked about a couple of slides back, we learned a sparse linear model. You could use say L1 regularization to make your model sparse, as you may have learned in machine learning. That's what we use here to be able to get these models to be sparse. So now why does that matter? You could now view explanations in Lime as a trade-off between the fidelity, which is the fidelity of G to F, which is given by the first term, and the complexity or the interpretability of the explanation, which is the second term. It may not be possible for both of these to be minimized. If you want G to be truer to F, you may need a more complex G. But if you make a more complex G, the interpretability could be reduced. So it could lead to this kind of a trade-off. But irrespective, if you chose a linear model for G, it does work fairly well in various settings. The last model that we will see here is inspired by what are known as Shapley values in game theory. This method is called SHAP and was introduced in NeurIPS of 2017. To understand this model, let's define a few notations. Let n be the total number of features in our method, in our setting. Let small v be a value function similar to attribution, but we'll see there's a slight difference. A value function that assigns a real number to any coalition S subset of n. By coalition, we mean a subset of features. Why are we calling it coalition? Because this is inspired from game theory. So in fact, an example where Shapley values can be used is, imagine a football team and you want to find out how important Messi is for, say, the Barcelona team, right? So if you want to find that out, you have a team already, let's say of 5 to 6 players, and you see if you added Messi to that, what value would the team now obtain with Messi and without Messi with the other 5 players, right? So that's so now that team is what we refer to as coalition. So in game theory, it could be players or any other context, but for us, each of those are attributes. We are saying that if we already have 5 attributes, if we now add a 6th attribute, how much is our value changing? That's what we want to measure. And phi sub v of I is the attribution score for a feature I. Given these notations, attribution score in the SHAP method is given by the marginal contribution that player, in our case a feature or an attribute or a dimension, whatever you want to call it, a marginal contribution that player I makes upon joining the team averaged over all orders in which the team can be formed. Let's again take the example of Messi. So if you wanted to understand what value Lionel Messi brings to the Barcelona football team, you consider the other players in the team and you consider them in all possible permutations and see if Messi is added, how the value changes. So you take first 3 players, add Messi, see how the value changes. You take 7 players, add Messi, see how the value changes. You take 7 different players, add Messi, see how the value changes. Average the value increase that you got across all of these possible subsets, and that's the value that Messi would bring to the Barcelona team. Formally, you would write this as phi v of I is equal to summation over all the subsets without Messi, without I, 1 by n prime, 1 by n factorial into s factorial into n minus s minus 1 factorial. This looks at all possible combinations in the subset without Messi, given n to be the total number of players or features for us. And this term here says v of s union I minus v of s. What if you added I to the team S minus only the team S without I? That's the value of adding player I to a coalition. So I hope you can translate this to understanding the usefulness of a feature in a neural network, but we have to answer one question: what is V for a neural network? What is that value? How do you measure that? So if you have a function f, which is a neural network, which is for predicting, then we're going to define V as V of S, which is where S is a subset of features, is given by expectation of P of x prime given xs, f of xs union x prime s dash. S dash is the complement of S. Rather, we are saying now that the value of a set S is given by expectation over all possible probabilities of picking elements x prime given a subset xs already, given a team of or a set of features s already, f of xs union x prime s dash. What would be the output if you added an x prime from s dash to xs? So you take all of those f's outputs, take the expectation that becomes the value of S here. But in this particular method of SHAP, we assume that the features are independent, which means this conditional probability simply becomes the probability of picking a particular feature from S dash, which is given by X prime. So you try to see, given an XS, what happens if you add a feature from X prime, and then what is the new output if you take the expectation of all possible X primes, that is the value of S. There's an extension of SHAP called deep SHAP, once again where the input features are assumed to be independent of one another and the explanation model is linear. But now the reason it's called deep SHAP is it's a combination of SHAP and deep lift, and you take a distribution of baselines and compute the deep lift attribution for each input baseline pair, and then you average the resulting attributions per input example to define your V or value function. Right? The value function, in short, the value function is inspired from deep lift. That's the idea here. The rest of it goes back and follows. So the final attribution score would still be given by this equation here. We are only now talking about how the V is defined using these equations. Having seen these different methods to be able to explain the decisions of CNNs or neural networks, neural network models, an important question to ask is, how do you evaluate these explanations? Do you have an idea? How do you check the goodness of these explanations? In all of the results that we showed so far, we showed qualitative results. So we took an image and said, look at this, it seems to work well. Right? But when you have a million images in your test set, you really cannot look at every image in that test set and study whether CAM is working better or deep lift is working better or deep SHAP is working better. You need some objective metric that averages the performance across all of your images. How do you do this? A simple way would be to take the intersection over union, IOU, of the thresholded salient region with a ground truth bounding box if it's available. So if somebody already told you that given an image, I have a cat in the image, but I also am giving you a bounding box around the cat. Let's say that's part of the data set. Then if my saliency map has a high intersection over union with this particular cat, what is intersection over union? We'll see this in more detail when we see other tasks such as detection in vision. But if that intersection over union is high, we assume that our saliency map or our method to compute the saliency map has worked fairly well. What else can we use? There's another metric that's been recently proposed in NeurIPS of 2018 and BMVC of 2018, which is called faithfulness. In faithfulness, we measure the correlation between the attribution scores and the output differences on perturbation. So we are trying to see is if you perturb an input and you see an output change, then, and if you see a significant output change, then the attribution of that input should also be high because that affected the output significantly. So the correlation between the attribution score and the output differences on perturbation should ideally be high. So here is the equation. We say that faithfulness is given by rho, which is the correlation of R, delta. R is the relevance of a particular pixel I, and delta is the output difference when xi is the image obtained after perturbing pixel I. Another metric which was defined in the BMVC paper here is known as the causal metric, and it has two variants known as deletion and insertion metric. Let's see the deletion metric, and the insertion metric turns out to be complementary. So in the deletion metric, you first delete pixels sequentially based on what our method says is most relevant first for a particular outcome. So if we think the pixels of a cat are the most relevant for calling it a cat, remove those pixels from the image. So replace it with a black pixel or a gray pixel. So remove those pixels from the image. And then you compute the AUC. I hope all of you know what AUC is. AUC is the area under ROC curve, which is a standard metric is used in several machine learning settings. So you compute your area under ROC curve of the network's output as, so the area under ROC curve you would know has two axes, where generally you vary some threshold and see what happens to a certain set of metrics that you're monitoring, and you ideally want your ROC curve to be something like this with a high area ideally. But in this particular case we see what is the function of the perturbed inputs versus the amount of perturbation. We're trying to see, as you keep increasing the perturbation, what happens to the function of perturbed inputs. Does it change a lot? As you vary x-axis, if y-axis changes a lot, then perhaps those pixels do have a high influence on the output. But because we have deleted the most relevant pixels, we would want the AUC to be lesser here after the removal of a particular pixel. So if you remove the most relevant pixel and plotted an ROC curve the way we saw it here, which means you perturb the input and see how much the output changes, and you plot this as a curve, you would want the AUC to be low after removing the most relevant pixel. You could also look at this complementarily and see it as an insertion metric, where you insert pixels sequentially, least relevant first. In this case, a higher AUC is better, just the way we spoke about it for the deletion metric. Another recent metric that's been proposed in NeurIPS of 2019 is known as ROAR. ROAR stands for remove and retrain. What the ROAR metric suggests is you get a saliency map for each image in your training data. You retrain the model after perturbing the most relevant pixels. The new model should have a large reduction in accuracy. So if you take an image of a cat, you know what saliency map you got for a cat, you now perturb all of those pixels, you should ideally see a reduction in accuracy of the model calling it a cat. That's the ROAR metric. There have also been some things called sanity checks for saliency maps that's been proposed. You're going to leave this as homework reading for you. And there's also a work that was published in ICML of 2017 known as axiomatic attributions, which defined a set of axioms for any of these attribution method. It says that any attribution method, be it GradCam, be it Lime, be it Deep Lift, all the different methods that we saw this week must satisfy certain axioms for them to be reliable in practice. What are those axioms? Once more, a homework for you to go back and read those axioms. To summarize this lecture, both deep lift and integrated gradients overcome the saturating gradients problem. Although deep lift is generally faster, because integrated gradients has to compute the data gradients across an entire path of different inputs. However, deep lift violates one of the axioms we talked about on the previous slide, known as implementation invariance axiom. Maybe you should try finding out why as a homework. Smooth integrated gradients are generally preferred over integrated gradients when sparsity is desired. For better interpretability in terms of visual coherence, XRAI is a good choice because it reasons at the level of regions rather than pixels. Lime is a model agnostic method. It can be used on top of any machine learning model because you're anyway going to approximate it as a linear model at the end. And it can be used for image data, text data, tabular data, so on and so forth. It is a bit slow because you have to train a model for every input image that you have, and it also sometimes is inconsistent between runs, but it is a model that's actually used by many companies today, in fact. SHAP has a strong game theoretic background, But to actually make it work, you have to use some approximations in the real world. So your homework is going to be about going through the list of axioms of attribution in this work. And for each axiom, try to find out the attribution methods that satisfy that. The methods that we have covered in this week that satisfy that particular axiom. Also go through the proposed sanity checks and experimental findings in this paper. Both of these papers are good reads. And from a programming perspective, play with Captum. It's a popular library for model interpretation by Facebook open source. You can also try visualizing any models that you've built in your assignments so far through the lens of OpenAI microscope for visualization and understanding. Here are some other resources. There's a very nice book by Christopher Molnar known as Interpretable Machine Learning. Covers all of these methods in more detail if you're interested. It's an online book. And there's also a collection of tutorials and software packages on this link that you see here. The references for this lecture are here.